Hi everyone. So today we have a couple of things to cover. We'll go over the normal approximation to the binomial distribution, which you'll need for the homework. We'll go through how to find the critical value, which is we usually take two standard deviations plus or minus above or below the mean, but sometimes you just want to have different confidence levels because two standard deviations above is roughly close to 95% confidence, but sometimes maybe you want to be 99% confidence that your mean is in the interval. So we'll go over that. And then finding the margin of error. So it should be margin. And finding the confidence interval. We'll be using a function that's already in the R help files. It's the web page is brianlukov.github.io. So this function is already there. We'll be using it here, and finding the sample size, which you'll need for, I think there's one question in the homework, so you need to find the sample size. Okay, so to start, so when you're using a normal approximation to the binomial distribution, you have to have enough samples, or the probability should be roughly close to 0.5. Now, when I say enough and it's close to 0.5, that doesn't really mean much. So that's why we have this success failure rule that basically says you should just check that n times p and n times 1 minus p, or q, which we usually use, that are both greater than 10. So if that's the case, then it's fine. So for example, in this case, it's 30 times 0.4, that's 12, I think. So let me just check. That's 12, and the other one was only higher because, well, it's 0.6 is more than 0.4, so that's 18. So both of them are greater than 10. So we're just roughly here near the limit. So we're fine with using the normal approximation, which means that the probabilities that we get using Q norm and P norm are going to be close enough to the binomial one. So the formula for the binomial distribution is you have the mean, which is n times p. So in our case, so if n is actually, so if n is 30 and p is 0.4, then n times p is 12. So for example, if we say that let's say that 40% of people are left-handed and we have a sample of 30 people, we expect about 12 people to be left-handed in our sample. Now the standard deviation is the formula for the standard deviation for a binomial distribution, which we'll be plugging into the normal approximation. So we just take a square root of p times 1 minus p divided by n, by the number of observations, and that'll give us the standard deviation. So basically, when we're doing the normal approximation, our mean is p times n, and oh, sorry, actually the proportion. Sorry, this is the proportion 0.4. So that's what we'll be using for normal approximation, and then the standard error. Sorry, so the standard deviation would be when you're not looking at n. And the standard error is when you're using n. So you're using the 1 over square root of n. So basically all you need to do is you need to use p norm, and you plug in p for the mean and SDE standard error for the standard deviation for the normal approximation. So for example, if I'm looking at what is the probability that when I take a sample that the proportion is going to be between 0.3 and 0.1, that's basically just this difference. So if you remember, actually a simpler case is if we're trying to see if the probability that it is below 0.4, that's basically just using p norm, right? Yeah, I'll give you. That's actually 0.5. Why? Because 0.4 is the mean of the distribution. So of course half of it is below that and half of it is above, right? And that's the same with this. So of course we can use different numbers like 0.3 and 0.6, for example. Oh, sorry, 0.3. Let's try both. So for example, this would be the probability that it's below, it's 13%, and it's above, it's, well, 1 minus that, so 86%. And if it's between the two values, between 0.3 and 0.1, just this. So sometimes you'll need to find the critical value, right? So let's say I have a confidence level. Let's say I want to be 95% sure that when I give you an interval, that the mean will be there. Well, technically, it's a more stringent condition. Like when you try to explain it in exactly what it means, it says that when you repeat the procedure infinitely many times, in 95% of the cases, what you're looking for, the true mean, is going to be inside the interval. That's the actual definition, but no one really uses it. So when they say 95%, they just kind of mean I need to be 95% sure. But although it's not actually correct technically. So you have the confidence level. You find the critical value very simply. So you say, so 1 minus the confidence level is 5%. Then you divide by 2 because you're looking at both sides of the distribution. And then you take Q norm of 1 minus that and gives you the critical value. For 95, it's something close to 1.96. Basically, if your value is 1.96 standard deviations above the mean, then that's the threshold for the 95% critical value. So if I use this formula I would get for the critical value, 1.959, so very close to 1.996. So the margin of error, so the reason we use the critical value is because we want to find the margin of error. So the margin would be the critical value times the standard error that we found. So this would be the margin. So for example, in our case, the margin would be 0.17. That means that we expect that 95% of the cases 0.4 plus 0.17 or 0.4 minus 0.17, that would be our margin. So just to look at this, so let's say, so if we plug the margin here, this is our lower and upper bounds on our interval. So we should expect it basically if we're looking at, let me run this just in case. Yeah. So basically we're expecting it to be, sorry, just one sec. Yeah, so we expect it to be between 0.38 and 0.41. That will be our expected, that will be our interval. Now, people usually use two standard deviations above or below because basically it's very similar. So if I run this, it's oh, sorry, yeah, I know it. So sorry, when we're actually doing, I already multiplied by the standard error here. So actually I just need P minus margin and P plus margin. So this would give me the actual values. That makes more sense. Okay. So we have the margin, we just do P minus the margin and P plus the margin. And that'll give you the lower and upper bounds, which is 0.22 and 0.57. If you use 2 instead of that 1.96, you'll see that when people just use 2 standard deviations above or below, it's very close to those values. So you can see that these are the 2 values we get for 2 standard deviations, and this is what we get with the actual 95% confidence level, etc., which is 2 very similar numbers. So we will just usually do 2 standard deviations above or below. But be careful in the homework because it says round to the 3rd or 4th decimal place, and it is going to be different. So use the exact confidence interval. Now, we have a function here already, which I'm going to run. So now the function is in my environment, so I can use the function. It'll give you the what we just calculated. As you can see inside the function, it does exactly what we went over. So it finds the critical value, and it finds the standard error. Well, these two are unrelated. So you can do either before that. And then the margin is actually combining these 2 values. It's the critical value times the standard error, right? And then, well, basically what this function does is does all of that what we did above for you, so you don't have to type that every time. So you just run this thing once, and then when you want to find the confidence interval for some proportion and some number of people n, and you want a 95% confidence level, you can just run this function. And you can see we actually get, well, the number that we calculated before. It's 0.22 something and 0.57. So if you want, so let's say we want a 99% confidence level. Let's say that we want to be not 95% sure, but we want to be 99% sure that the proportion is inside the confidence interval. What would you expect? Would you expect a bigger interval, or would you expect a narrower interval? What do you think? So if we want to be really sure that our interval actually has the value, you can just make it bigger, right? Intuitively. If you want to be really sure, like if in the limiting case, if I want to be 100% sure that the proportion is inside my interval, I'll just make the interval as big as the whole real line, right? From like minus infinity to plus infinity. So if you think about it, that well, it's just gonna have a bigger interval. So if you want to be 99% sure, well then you have a bigger margin. So you also need to find the sample size. So let's say you have a confidence level. Let's say you want to be 95% sure that basically you, within this margin of 0.1, that you have the interval. So you want to be 95 sure that the proportion is inside the interval, but you want to fix the size of the interval. So before we had n as a fixed number, like number of observations, and we had a confidence level, and we found the margin. But here we can go the other way. We can say, look, I want the margin to be, so I want to be plus or minus 0.1 margin, and I want to be 95% sure. But that means that I'll have to maybe poll more people for my poll, or have a larger sample of people that I picked from the population. Well, you can actually find this using this equation. So it's very simple. If you just look at the equation, you can just basically turn around where we have the margin equal to something divided by square root of n. We can just put the square root of n on the other side and then put the margin on the other side. And if you manipulate it, you'll get this equation, which is it's basically the same thing. It's p times 1 minus p times the critical value, z star, divided by the margin squared. So you can just do this by hand. If you do this like mathematically, you just get the same. You just get this equation. So if I run this, I should get some sample. So here it says my sample size should be 96.03. That means that it should be greater or equal to 96.03. Because this is a number that's not actually an integer, you would just use the next largest number. So if you want to be 95% sure, if you use 96, you won't be exactly, you'll be a little bit less than 95% sure. So just use this number that you get, round up to the nearest integer above. So for example, if we have the margin from before, let's say that the margin was this. So if I try this, I should get the n that I had before. So in our case, p was 0. No, actually, p was something else. Oh, 0.4, right. We have p 0.4, we have 30, and then we want to find the margin. So the margin would be 0.175. So let's say we plug that in, and we plug the 95% confidence level, and then for p we plug what we had, 0.4. We should get n to be equal to 30. Well, close. Oh, we get exactly 30. So that means that our method works, right? If we plug in our result for the margin and then try to find what n is, we actually get the same n. So that means that this is like the inverse procedure. So in your exercise, sometimes you don't know the proportion. Actually, you might not know it, but you want to be conservative in your estimates. So if you want, to be conservative, that means to have the largest margin, but still you want to have a good margin. But let's say you're not sure. So for example, if you put 0.5, that means that you get the biggest margin. So people usually use 0.5. So I think in one of the homework questions you might need to use that. Other than that, I think that's mostly it. So you need to understand the normal approximation, and you must check that basically it obeys the two rule. Actually, I think there might be 3 rules, but the 2 rules that are necessary here is that you need to check that the n times p and n times 1 minus p are greater than 10, both of them, and you should see that you should check that the sample is not more than 10% of the population, which is, I think it's most of the time it's actually fine. So it's not more than 10%. So this is what you need to find: the critical value, the margin of error, and you can just use this function for the confidence interval. And you'll need to find the sample size in one of those questions. So other than that, I think that's most of what you'll need for the homework. Are there any questions? Anything that's unclear, maybe? Yeah.
So the STA is standard error.
Yeah, I just call it standard error. Yeah, you can I guess here in the function this doesn't, like this here that you see inside the function, you don't have to care about this because it's all inside. When you use the function, you just run this part, ci.prop, and then you give it the numbers. You don't care about the names here inside. So just to clarify.
So all of the ci.prop and the z star, that's already in part R?
No, so this is a helper function that's been written for this course that you can just use. basically when I'll be uploading the script anyway, so you can either find it on the help pages for Stat309 on that Brandon Lukoff GitHub page, or you can find it in the script that I'll upload anyway. So you can just copy paste the function and basically just copy paste this, and then when you run it once, it's going to be inside your environment here. So for example, let me just show you. So now it's empty, but I just need to run this once, and then I'll have the function here. So if it's here, then I can use it. So you can't really see, but it says, okay, see that prop. And then I can just run this line here, and it'll work. But before, okay, so since I deleted everything, I don't have a P or an N. So let me just put some, let's say P0.4 and N is 30. So I should get the, so now if I run the function, yeah, I get the numbers from before. So that's all. Does that answer your question? Okay. I attach it so I upload the YouTube video and I post an announcement to both sections, and it's attached in the announcement. Yeah, that's for every week actually. Any other questions? Anything else unclear with the homework? All right. Well, I'll be uploading it.